Hey students, in this video we're going to cover solving trigonometric equations. It's the first lesson of Unit 2, which is Analytic Trigonometry. We have an outline where for lesson 1 we're solving trigonometric equations. You can see the rest of the lessons. We have an overview, important information. We have a unit test that would be scheduled for March the 18th. We have one formative assessment that is the Delta Math homework set that will be up. We have 2 quizzes, a lesson 1 through 3 quiz and a lesson 4 through 6 quiz. In this lesson, we're going to review the reciprocal identities, quotient identities, and the Pythagorean identities. We're just going to look at the formulas. And in this lesson, we're going to learn the even odd identities, and we're going to learn how to solve a trig equation by hand, which we say analytically, and we're going to use a graphing calculator, probably Desmos, to solve an equation that can't be solved by hand. The main idea here is that we're just using algebraic techniques, isolating, factoring, and factoring quadratic forms to solve these. And again, anything we can't solve by hand, we're going to use a graphing calculator. All right, so a quick review of the trig identities. We're going to need these just moving forward as we do subsequent lessons. We have the reciprocal identities where cotangent is 1 over tangent, cosecant is 1 over sine, and secant is 1 over cosine. With that, we could add sine is 1 over cosecant, that's a C. We can have cosine is 1 over secant. We won't see these, we won't use these much, but just to say we have them. And tangent is 1 over cotangent. So those are the reciprocal identities. Of course, tangent is sine divided by cosine, and cosine is cotangent is cosine divided by sine. We have our 3 fundamental Pythagorean identities. Sine squared plus cosine squared is 1. Tangent squared plus 1 is secant squared, and 1 plus cotangent squared is cosecant squared. You can find these in the notes for Unit 1. We still have all of these. New is the even odd identities. Cosine negative x is just the cosine. You can drop the negative. Same with secant. The sine of negative x. For all of the odd functions, if the angle is negative, you can displace the negative beside the trig function, and you get the opposite sine trig value. We have examples for this, so it'll make sense when we see it. All right, so for the first example, we have the sine of negative 30 degrees. Now, sine's an odd function, so this is the equivalent of, let's use a different color. Let's go with, we'll go with this blue, okay. So we'll erase this, go back to blue. All right. So sine negative 30, we can zoom in a bit, is negative sine of positive 30 degrees. And we know that the sine of 30 is a half, so negative sine of 30 is negative 1/2. Cosine of negative 7 pi over 4, now cosine is an even function, so the cosine of negative 7 pi over 4 is the same as the cosine of 7 pi over 4. So 7 pi over 4, that angle is in quadrant 4, and cosine is positive in quadrant 4. And if you know the unit circle, this would be the square root of 2 divided by 2. Now notice I say give the exact trigonometric value. So you can't give me the decimal. Tangent negative 4 pi over 3. That is tangent is an odd function, so that's the same as negative tangent 4 pi divided by 3. If you remember tangent 4 pi over 3, tangents, this is going to be in quadrant 3 because that's 240 degrees, and the tangent of 240 is square root 3, I believe. So this is just going to be negative square root 3. So that is how we use those even odd identities. We're going to use those for one of these problems, but just a quick review for that. All right, so now the first example of actually solving a trigonometric equation, we're going to do by simple isolation. So we get 2 cosine x minus square root 2 equals 0. So we're just going to isolate the trig function. So we're going to add square root 2 So we add square root 2 to both sides. We get 2 cosine x equals the square root of 2. So cosine x equals the square root of 2 divided by 2. And so this is why we learn the inverse trig functions. So we know that to solve for x, we're going to have x equals cosine inverse square root 2 divided by 2. Now, unless you're told otherwise, you should assume that your output is going to be on the interval 0 to pi, because that's where inverse cosine is going to be defined. So from 0 to pi, the only angle with the square root, with a cosine of square root 2 over 2 is pi over 4. We are giving our angles in radians, not degrees. So pi over 4. Now, if we had the interval 0 to 2 pi, we would have pi over 4, and cosine again is positive in quadrant 4, so then we would also get 7 pi divided by 4. But unless you're told a specific interval, always assume the interval for which the inverse trig function is defined. So that's going to give us just pi over 4. Second example, we have 3. Oh, that should be, this should be a 2. My apologies. That should be a 2. I don't know. I didn't catch that. So 2 sine x plus, no, I'm sorry. I take that back. It's fine. I didn't see the other side of the equation. My apologies. That's fine. So we have 3 sine x plus square root 3 equals sine x. So in this case, we're going to combine like terms. So that means we can subtract a sine x from both sides, and we would get 2 sine x plus the square root of 3 equals 0. And that would mean that 2 sine x equals negative square root 3. So sine x is going to equal negative square root 3 divided by 2. And so again, we're going to apply our inverse trig function. And this time we're going to write it like arc sine, just so we can get, remember that that's equally as valid as the sine inverse you see on your calculator. So x is arc sine negative root 3 over 2. And so remember, inverse sine is defined on the interval negative pi over 2 to positive pi over 2. So the angle that has a negative, a value of negative root 3 over 2, sine value, that's going to be x equals negative pi divided by 3. Now again, if we want an interval 0 to 2 pi, so this is on the interval negative pi over 2 to positive pi over 2, that's the only answer. But if we change our interval, for instance, to 0 to 2 pi, we would get, so sine is going to be negative, so that's going to be quadrant 3 and quadrant 4. So we would instead have 4 pi over 3 and 5 pi over 3 on those intervals. But again, unless you're told to use a different interval, always use the one that the inverse trig function is defined on. Example 4, we are isolating a squared function. So cotangent squared x minus root 3 equals 0. This is the same as, I'm sorry, this should just be a 3. Mr. Moore, you made a terrible mistake. This should just be 3. And it's cotangent, not cosine. So that should be cotangent squared x minus 3. My apologies. So we should get cotangent squared x equals 3. And so then we're going to take the square root of both sides. So cotangent x is going to equal positive and negative square root 3. Now, we don't have a cotangent. Like, it's easier to do this in terms of tangent. And so if cotangent equals this, then tangent x is going to equal plus or minus 1 divided by the square root of 3. Now, in a unit circle, we'll know this as plus or minus square root 3 divided by 3. So that's what tangent equals. So in this case, x is going to equal tangent inverse of square root 3 over 3, or x equals tangent inverse negative square root 3 divided by 3. So in either case, we should know that this positive square root 3 over 3 is going to give us pi divided by 6, and negative tangent inverse of negative square root 3 divided by 3 is going to mean x equals negative pi over 6. Again, if we put these in intervals from 0 to pi over 6, from 0 to pi over 2, we're going to get all of the multiples of pi over 6 in the range from 0 to 2 pi. So on the interval 0 to 2 pi, x would equal, so just all of the multiples of pi over 6, only the multiples of pi over 6. So pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Those would be the four answers if we were on the interval 0 to 2 pi. But again, because we are bound by the domain of the range of the inverse tangent function, remember inverse tangent is defined on the interval negative pi over 2 to positive pi over 2. Example 5 is an example in which we can factor. So let's see what that looks like. So when we factor, we're going to group our terms on one side. So we would get tangent x times sine squared x minus tangent x equals 0. Both of these have a tangent in common, so we'll get tangent x times sine squared x minus 1 equals 0. So we have two possibilities. So either tangent x equals 0, which means x equals tangent inverse of 0. So tangent is going to be 0 where the numerator equals 0. So remember, tangent is sine x divided by cosine x. So the only time a fraction can equal 0 is when the top equals 0. So essentially, we're looking for when sine is equal to 0. Now, in the unit circle, we know sine is going to be 0 at 0 degrees and at pi radians. So again, we're thinking on the interval negative pi over 2 to pi over 2. So x is just going to equal 0 radians. We'll put radians so we don't confuse that one with degrees. The other possibility is that sine squared x minus 1 equals 0, which means that sine squared x equals 1, which means that sine x is equal to positive and negative 1, which means that x equals either sine inverse of 1 or sine inverse of negative 1. In the case of x equaling sine inverse 1, you need x is going to equal pi over 2. In the case of sine inverse negative 1, x is going to equal negative pi over 2. So our three solutions are 0, pi over 2, and negative pi divided by 2. Example 6, we are factoring a quadratic form. So imagine we did a substitution for a moment where we say what letter doesn't look like x. So we'll say like w. So we're going to say w equals cosine x. You don't have to do it this way. I'm showing you a way if the trig functions make you see stuff that's not there. You can use a variable to replace it. So now if we use w as a replacement for cosine x, we would get 2w squared plus w minus 1 equals 0. So now this is something we know how to factor. This would be 2w times w, and then we need factors of a negative 1. So we're going to have negative 1 and positive 1. So we can check that. It would be 2w minus w. That would give us the w in the middle. You could also factor by grouping. I'm not going to do that because It's too much work when we can actually just kind of remember this factor. So we end up with 2w minus 1 times w plus 1 equals 0. Now, if you want, you can go back and replace, so we'll solve this all the way out. So if 2w minus 1 equals 0, so 2w minus 1 equals 0 implies that 2w equals 1, which implies that w equals a half. So remember, w, we made cosine x, so that's saying cosine x equals a half. So x is equal to cosine inverse of a half. And that's going to mean that on the cosine inverse defined on the interval 0 to pi, so that's going to mean that x is equal to pi divided by 3. The other possibility is w plus 1 equals 0, so w equals negative 1. And remember, again, w was cosine x, so cosine x equals negative 1, x equals cosine inverse of negative 1, and in that case, we're going to get x equals pi. So our two solutions are pi over 3 and pi. Now, you don't have to use the whole w factoring method. We could just straight out factor this to be 2 cosine x minus 1 times cosine x plus 1 equals 0. And just know that when you're factoring a quadratic, the term that's in the middle without the square, that's what goes inside your parentheses. In this case, because you have to multiply cosine by itself to get cosine squared. So really, whatever the power should be half of that, the largest power for quadratic form, but some people like doing it this way instead, however you want to. So example 7, we're going to rewrite this in terms of a single trigonometric function. So notice we have a cosine squared x and we have this sine negative x. Both of those are going to present a slight problem. So we're going to use the identity 1. So we know 1 is equal to sine squared x plus cosine squared x. Now it won't take much work to turn cosine squared into... So we get cosine squared x is equal to 1 minus sine squared x. That's what we're looking for. Fantastic. So the first replacement we're going to do is cosine squared is going to be replaced with this. So we're going to have 2 times 1 minus, 1 minus sine squared x minus, so you remember sine's an odd function, right? So the sine of negative x is going to be negative sine x. So we can turn this into plus 3 sine x. All we did was take this negative and multiply it here because sine's an odd function. And minus 3 is going to equal 0. So if we keep simplifying, we get 2 minus 2 sine squared x plus 3 sine x minus 3 equals 0. And say we want our sine squared to be positive, then all of this stuff needs to move to the right, or we can multiply it all by negative 1. But first, the 2 and the negative 3 are going to make a negative 1, so we get negative 2 sine squared x plus 3 sine x minus 1 equals 0. So we need to... all right, so again, we're going to just multiply everything by negative 1. So we get 2 sine squared x minus 3 sine x plus 1 equals 0. We just changed the signs of everything. So we're going to factor this to be 2 sine x. How do you get 2 sine squared? You have to multiply 2 sine x times sine x. And then the only factors of positive 1 that can still give you a negative in the middle are going to be 2 negative 1s. So we end up with 2 sine x equals 1, which means sine x equals a half. And so x is going to equal sine inverse of a half. So x equals pi divided by 6. I'm back at school. Announcements coming. I'm sorry.
A ninth grade student in your class.
I'm sorry.
And we have not picked them up for a tour yet. Please send them to Commons A right now. Again, again, if you have ninth grade students who
Yeah,
have not
just
been picked up for a
pause
tour, please send them
and
to
skip
comment
or
A
something.
right now. Thank you.
Okay, and so the next part is sine x minus 1 equals 0. So that means that sine x equals 1. X is going to equal sine inverse of 1. And so x is going to equal pi divided by 2. So our two solutions are pi over 6, pi over 2. The two techniques we applied here were we applied a Pythagorean identity, and we also applied an odd or even identity to reduce this to a single trigonometric function, in this case sine. Our next example is using the next two, well, just 8 is going to use inverse trigonometric functions. So we have secant squared x minus 2 tangent x equals 4. Again, anytime you see a squared in a different trig function, you probably want to apply a Pythagorean identity. So remember, tangent squared x plus 1 is equal to secant squared x. So we're just going to turn secant squared into that. So tangent squared x plus 1 minus 2 tangent x equals 4. We are going to subtract 4 from both sides. So we get tangent squared x minus 2 tangent x, and 1 minus 4 is going to be negative 3, so that equals 0. And this is going to factor using tangent x this time. So tangent x, how do you get tangent squared? You multiply tangent by itself, so you get tangent x plus something times tangent x plus something else. So factors of negative 3, they give you a negative 2. That multiply to be negative 3, that adds to be negative 2. We're going to say minus 3 and plus 1. So we get tangent x equals negative 1. So x is going to equal tangent inverse of 1, negative 1, which means that x equals negative pi divided by 4. And then we get tangent x equals 3, or x equals tangent inverse 3. So tangent inverse 3 is not one of those special angles that's on the unit that we have on our unit circle. So this is one we have to graph by, we have to do on the calculator. So we're going to, again, we're in radians. Make sure your calculator is in radian mode, and we just do tangent inverse 3, and we get 1.249. So x is 1.249 radians. All right, so the last example you can do on a TI graphing calculator, or I would recommend using Desmos. So we have this x equals 4 cosine x. Now, on all of these other examples, we didn't have an x like by itself in the equation. The x was the angle. In the case of number 9, x is both the angle right here for cosine, and it's out here by itself, which means you can't isolate the trig. You can't isolate the angle by doing inverse trig stuff that we've done on all of these other examples. When that happens, the easiest thing to do is use just use a graphing utility to solve this. So the only thing that we need to do is put this in the form where it equals 0. So we're just going to have x minus 4 cosine x equals 0. And we want our answers in the range of negative pi to pi. So that's like negative 3.14 to positive 3.14. And we're just going to pull up Desmos here. So where do I have Desmos? Desmos right here. So we want, it was x minus 4 cosine x. So x minus 4 were the functions, minus 4 cosine x. And again, we want in the range from negative pi to pi. So anytime it crosses the x-axis in that range. So one of the solutions is negative 2.133. The other one is 1.252. So let's go back over to the notes. So we get x equals negative 2.133, and the other solution was x equals 1.252, I believe. Is that correct? 1.252. All right. So that is how you solve the equation if you can't solve it by hand, and this cannot be solved by hand. All right. So that's our video. That's our lesson on solving trig equations. We covered most of the types that we'll solve. Next video we'll cover the sum and difference formulas, and then we'll solve equations using those identities as well. The summary is here, where all we did was use basic algebraic techniques, identities, and quadratic form to by hand solve these. And when we couldn't isolate the angle, we used graphing